Okay, problem number 8. I know we skipped some numbers here, but I took a whole page out of your packet, so you can thank me later. Here we have this graph. It says it's showing the same ball dropped on two different planets. Part A asks you which planet makes the ball accelerate more. So as you look at the curve of those, you're looking to see which one has that effective gravity the most. And you're looking how that position changes over time. It's pretty obvious to see that planet A, or part A here, has a lot more bend to it. So most of you could have guessed it is that planet A that has that greater effective gravity. It will accelerate more. Let me get a marker that's a little less fat there. Okay, so planet A, and for your explanation, simply put that has a greater curve on the graph. Okay, for part B, we have to find at a time of 5 seconds what is its velocity on planet A and on planet B. So this is not quite as simple as it looks. What we have to do is set up those windows that we've been using in class. Now on the lab and yesterday in class, we've been doing that with a data table. We don't have a data table here to work with, so we have to do that on the graph. So let's start with planet A. Do that in blue. So with planet A, we're looking at a time of 5 seconds, what is its velocity? What we have to do is set up a window that is centered at 5 seconds. So a nice window we can use is from a time of 4 to a time of 6. What we're going to look at is at a time of 4, its position is right here. At a time of 6, the position is a little bit down there. What we're going to try to do is find the slope of the line that would connect those 2 points. Let me go ahead and make that for you. So we have to find the slope of that straight line. That slope will equal the velocity at a time in the center of the window, which we centered at 5 seconds. Okay, let's go about doing that. So for planet A, our velocity will equal our distance that it drops, delta y, divided by the time that it takes, delta t. The distance it drops, it starts at this point right here. That's at a position of -10. It drops down to this position there. It's just past 20. If I had to guess, I'd say about 22. So from 10 to 22, it dropped down a total of 12 meters. So delta y for planet A would be 12. It did drop down, so we're going to add a negative to that value, divided by the time it took. Now this window that we made was from a time of 4 to a time of 6. So from 4 to 6, it dropped down 12 meters. It took it 2 seconds to do that, from 4 to 6. So delta t for this problem will be 2. -12 divided by 2 gives you that velocity. -6. Your label will be meters per second, since that's what we have from that graph. Okay, now you're going to be doing the same thing for planet B. So I'm going to erase this on my graph and get a green marker, how about? So we're still looking at a time of 5 seconds. So at this 5-second mark, we're looking for what is the speed on planet B. So we set up our window, still set up a window from 4 to 6, give you nice numbers to work with. You're looking at a position of At a time of 4, it's at this position. At a time of 6, it's down here. Your job is to find the slope of that line that connects those 2 points. So use the same method kind of that we did on planet A and find the speed at 5 seconds for planet B.